Okay, this video is going to be talking about the mean value theorem. And the theorem says that if f is a differentiable function on the interval a to b, now really probably what it would say in your textbook is that it's continuous on the closed interval and differentiable on the open interval, but that's not super important. Then there will be a point on the interior of the interval for which the average rate of change over the interval is equal to the instantaneous rate of change at that point. Okay. And so, what is this actually saying? And I'll give you kind of more of an equation that you can think of when you see mean value theorem here in a second. But as far as its actual meaning, where the average rate of change is the slope of the secant line. It's the slope of the line that connects them. It's rise over run. Familiar with that? Now the instantaneous rate of change, what kind of slope is that? Yeah, the slope of the tangent line. So if the slope of the secant line is equal to the slope of the tangent line, well, that would mean that they're parallel. So there's going to be some place where the tangent line is parallel to this red line. And I kind of see one over here. You know, this is very approximate here. But I also see another one over here. And the number of relative extrema will probably somehow affect the number of places. Wow, on screen I can see that that was really not a great sketch. But, you know, there definitely is. You can see that there's one. Okay, the proof of this theorem is pretty interesting. I was thinking about it last night. It's something that I'm not going to include on this video, but I might discuss with y'all after lunch today, provided that there's time. Then there's the special case where f of a is equal to f of b. Okay. Oh, I didn't actually give you a formula to, you know, consider, and so, no, not distribute content. Oh, goodness. Okay. Man. Okay, what you're going to see when you see the mean value theorem, you're going to say to yourself, well, I know that that means that there is a place where f prime of c equals f of b minus f of a over b minus a. That's kind of the relevant formula for the mean value theorem. Okay, so take the derivative. You'll see where it equals the value of the average rate of change. Okay, if f of a equals f of b, let me draw a picture of that happening. And this is, you know, some y value. Okay, if they have the same y value, then the average rate of change, f of b equals f of a, f of b minus f of a equals 0. b minus a is non-zero, so that average rate of change is 0. Meaning that there has to be some place in the interior of the interval, at least one place, where the instantaneous rate of change is 0. So let me draw it. Okay, so I'm going from a to b continuously and in a differentiable way. I can try to avoid it, but I eventually, you know, I have to come back. Right? I could, okay, that it happened. Okay, there was a flat spot. Okay, I can really try to avoid it as long as possible. But if I'm going to go up to f of b in a smooth way, it's going to have to curve up like that. Even that looks kind of like a sharp corner. Now, if there's a sharp corner, you can see that there needn't necessarily be a place with a flat derivative. If there's a discontinuity, there definitely wouldn't need to be that. Okay, so whoops. I think the best way to illustrate it, though, is just, you know, kind of make it something looking like that. And, you know, we say that the slope of the secant line is flat, and the slope of the tangent line is flat, maybe somewhere around there. Whoops. Missed, but it'll be all right. All right, for our first example, let's just look at trig. We haven't looked much at trig today. We've been doing a lot of polynomial stuff. So f of x equals sine of x on the interval 0 to pi. And oftentimes how this question will read is find the value of x that satisfies the conclusion of the mean value theorem for f of x equals sine x applied to the closed interval 0 to pi, or something like that. Okay, so what we say is that f prime equals f of pi minus f of 0 divided by pi minus 0. We can do that. Okay, so that's going to be sine of pi, sine of pi is 0, minus sine of 0, also 0, over pi. Okay, so that's just 0. So we're interested in where f prime of x equals 0. Well, we know what f prime of x is. F prime of x is cosine of x. And so we know, and we also know where cosine of x is equal to 0. Now we're only interested in the interval 0 to pi, so I'm only going to give us that part of the unit circle. And so we're, meditating on this part of the unit circle. We're thinking, where is cosine equal to 0? Well, that happens to be where the x-coordinate is 0, which would be right there. Okay, so that means we have x equals pi over 2. Okay. Pi over 2 is the place where the average rate of change is equal to the instantaneous rate of change. Now I'm also going to draw you a picture of this just because, we can. It's pretty easy. It's going to kind of draw you a picture of sine x on the interval 0 to 2 pi. We're actually only interested in the interval 0 to pi, but why not? Remember that sine is the one that starts in the middle and goes up. So there we are. Okay, these are the axes. That meaning this would be pi and this would be pi over 2. Okay, see here, the slope of the secant line is 0. And up here at pi over 2, the slope of the tangent line is 0. Okay, so this is just, showing you how that works. Okay, then we've got this function. We've got absolute value of x on the interval negative 2 to 4. So, why don't I just draw a picture of that? Maybe I'll say that's negative 2 and this is 4. So it's going to go like that and up like that. Okay, so we're interested in a place where g prime of x is equal to g of 4 minus g of 2 over 4 minus 2. Okay, so that looks like g of 4 minus g of negative 2 over 4 minus negative 2. Okay, so that's equal to 2 over 6. Okay, so we're interested in a place where g prime of x equals 2/6. Now, we may not have talked about the derivative of absolute value of x, but the derivative is a function that you've seen before in this class. Okay. Remember the derivative of absolute value, well, the slope of it is 1 on the right side and negative 1 on the left side. So g prime is given, you could give it as a piecewise function, 1 and negative 1, where x is greater than 0 and x is less than 0. And the way that we wrote, kind of an explicit formula for this function was we said that was absolute value of x divided by x. But we know that absolute value of x divided by x is only ever equal to 1 or negative 1. So how am I supposed to make that equal to 2/6? What's going on here? Yeah, it's not differentiable. Okay, so that kind of that if statement at the beginning of the theorem is super important, right? If the function fails to be differentiable, we can't guarantee that there will be a place where the slope of the tangent line is equal to the slope of the secant line, right? Our only options for slopes of tangent lines are over here 1 and negative 1, and you can see clearly that neither of those blue lines are parallel to the red line. Okay? It's important to check the conditions of the theorem before you start to go try to apply it. Okay, then the last thing is, here we have a picture of a differentiable function, and it's going to ask us to find the values of x to satisfy the conclusion of the mean value theorem on the closed interval negative 5 to 3. So one thing that would be important here is to kind of count the little tick marks. So negative 1, negative 2, negative 3, negative 4, negative 5. Okay, here is 3. So it wasn't actually asking us for the full thing. Okay, so here, the slope of the secant line is 0 because, well, I'm just connecting the dots. I can see the slope is 0. And so we're looking for places where the tangent line is flat. And so that would probably be this one and this one. So this would be x equals 2 and x equals -3. Bless you. Video.